Okay, good morning everyone. Welcome back. So we have been talking about power flow analysis using Newton-Raphson method. So I want to remind you the basics of Newton-Raphson method, and today we will discuss the variation of that, which is called dishonest Newton-Raphson, decoupled power flow, and fast decoupled power flow, and finally DC power flow. Okay, and you will have some more homework today, due by, today is Tuesday, due by next Tuesday, okay? So yeah, these are power balance equation. This is for active power and this is for reactive power. And so we have P, Q, I is the node index, so you remember this. And then using this, we constructed a vector function for each bus, P 2, 3, n, Q 2, n. So the slack bus is removed here, and our variable is theta and voltage magnitude. So variable is a vector and function is a vector, and we want to find the solution of f of x equals 0 numerically. So this is the update rule. The next guess is updated using the Jacobian. The Jacobian is a gradient of a vector function. The inverse of the Jacobian at some point. Okay, so this is a linearization technique. And the difficulty of Newton-Raphson is to compute the inverse of this Jacobian matrix. So that's why we need to discuss variations of Newton-Raphson. So mostly this is about how to easily or approximate the inverse of this Jacobian matrix. Okay? So yes, Jacobian matrix is like that, and then you have an example. I hope you solve this homework problem successfully, blah, blah, blah. And this is the region of convergence. Now, the high voltage convergence region, low voltage convergence region, yellow, this is undesired part. And this black dots means diverge case. Okay? And I think this is interesting. And we will see similar figures also in a moment, but when you focus on this area, diverge, convert to low voltage solution, diverge, convert to high voltage solution. So very, very sensitive with this area, that area. Okay, so later, if you have a chance to solve power flow equation using Newton-Raphson or some other method, if we are here, then that method is robust. But if you are somewhere here, then please be aware that the solution can be sensitive. Okay? So PB bus case, blah, blah, blah. Voltage dependent source. Okay. So using Newton-Raphson method, standard Newton-Raphson method, the power world solves this kind of 50 bus system, I don't know. So, by the way, did you have a chance to do this kind of homework already or not? Some of your homework due on this Thursday, does that have using power word or not? No, not yet? You will have that, okay? So yeah, by hand, you solve just 2 bus system or 3 bus systems, but for larger systems, you need to use power world simulator or something like that. Okay, so next topic is dishonest Newton-Raphson. And since most of the time in the Newton-Raphson iteration, is spent dealing with the Jacobian. So one way to speed up the iterations is to only calculate and factorize Jacobian occasionally. Occasionally means from time to time, not all the time. So we don't want to compute Jacobian at every iteration. And So that method is called dishonest Newton-Raphson. Okay? The Jacobian is not computed at every iteration, but occasionally. And an extreme example, yeah, this is really extreme. An extreme example is to only calculate the Jacobian for the first iteration. Yeah, at x0. Okay, and that is called chord method. Okay, so the honest Newton-Raphson update rule is this. We discussed this last time, and this honest Newton-Raphson is that, especially the most extreme case. No, it is not updated at 0 iterations. So once you compute Jacobian and once you compute the inverse of the Jacobian matrix, our variable x, the theta and voltage magnitude, is updated in this way. So sometimes it works well. Okay? And the stopping criteria is same as before. So this is an example. This honest Newton-Raphson, and just for simplicity, our example is f of x is x squared minus 2. So the root is square root of 2. And applying this honest Newton-Raphson is this. The update of variable is the inverse of the gradient times the function value. And derivative at x equals 0 is what? The initial, not x equals 0. So at 0th iteration, it depends on the initial value. Anyway, the derivative is 2 times x, so the inverse of that is that. Anyway, this is fixed, and x is updated in this way. So if you think, hey, does it work? Why does it work? If you think like that, this is x, and f of x, square root 2. So the function looks like this, and this is square root 2. And the intuition of Newton-Raphson is if you start from here, draw a straight line, and then go to this point and draw another straight line like this. But if this slope is constant, yeah, this is just constant. Okay? So rather than it changes, it is constant, but it works. It works in this simple example. Okay? So this is the iteration, honest Newton-Raphson and dishonest Newton-Raphson. So as the iteration goes on, the solution converges anyway, and slightly different, but not that much. Okay. So we pay a price in increased iteration. Yeah, the number of iteration gets larger, but decreased computation per iteration. Okay, we don't need to compute the derivative all the time. We just use the initial derivative only. Okay, so we can save that computation time, even if the number of iteration increases. Okay, so that method is called dishonest Newton-Raphson method. So, your previous example about two bus systems, the region of convergence looks like this. High voltage solution and low voltage solution and diverger case. Actually, it looks more robust than the previous case. No, previous case, you see. I think this is quite interesting. How can we have this kind of beautiful patterns? In the case of dishonest Newton-Raphson, we cannot observe those patterns. What does it look like? Phantom of Opera. No, sorry. Okay, and yeah, this is the region of convergence of honest Newton-Raphson. Compare this with that. So the region ROC is reduced, but anyway, okay, you see the difference. Next topic is this one, decoupled power flow. this decoupled power flow means that our interest is P, Q, and theta, and V, I. Okay, so active power is a function of angle and voltage magnitude, as well as reactive power is also a function of angle and voltage magnitude. But mostly, we will see that this is related with the active power is related with the phase angle, actually phase angle difference between two buses. The power flow between I and J depends on the phase angle difference between these two buses. And this reactive power is mostly dependent on the voltage, or voltage is dependent on the reactive power. So you may remember that, in the beginning of our class, when we talked about power factor compensation, we need to inject reactive power at the load side by adding capacitor, okay, or capacitor bank. So that is because this reactive power mostly determines this voltage. So that's why this professor studies voltage and reactive power in the distribution network. Okay, so we will see why that is. Okay. So the completely dishonest Newton-Raphson or code is not usually used for power flow analysis. However, several approximations of Jacobian matrix are used that result in a similar approximation. And one common method is a decoupled power flow. So in this approach, approximations are used to decouple the real and reactive power equations. Okay, so let's see. Okay, the notation is slightly changed. So in previous case, okay, our previous, what am I doing? Okay, this is page 131. Okay, okay. Yeah. 131. Active power and reactive power. So that was our notation. And how can I go back? Yeah, here, okay. So the new notation is just delta Q and delta P and delta Q. But in previous notation we didn't have this delta term. Okay, so Q or delta Q, they are same. Don't be confused. And also in previous notation we explicitly use PI for each bus. But here, that function delta P is a vector function of all the active power, and Q, delta Q is is also a vector function, reactive power for all nodes. So our f of x is f of x consists of those two. So this is Jacobian matrix. Jacobian is gradient of our original function, and that P and Q are a vector function. So that notation, actually, when this is this P is a scalar, this is just gradient. But if this P is a vector, itself is a Jacobian matrix. This is just a notation. So some guy uses this kind of notation for Jacobian. Okay, so this is a matrix. This is matrix. Okay, so this notation is same as before. So we have a Jacobian matrix, our optimization variable, and the function. Okay. So delta P is defined like this. Similarly, delta Q is defined in this way. Okay. So anyway, our variable x is theta and voltage magnitude. And so let's focus on this part. And what we want to have is that this is mostly 0. I already told you the result. Voltage, active power depends on phase angle, and reactive power depends on voltage, which means, you know, we have very loose connection, and we have a very loose connection between these two. That means if you take the partial derivative, if you compute the Jacobian of P with respect to voltage magnitude, that is almost 0. Similarly, if you compute the Jacobian of reactive power with respect to phase angle, that is also almost 0. So let's see why. Yeah, this is just the result, okay? So 0, 0. And we have this relationship. And so computing the inverse of this matrix is easier than computing the original Jacobian matrix anyway. So using this update rule, the delta theta. So what is the advantage of using this kind of decoupling? So this times that equals that, and this times this equals that. So you compute the phase angle update and the voltage magnitude update separately, decoupled, and you only need to compute a smaller size of Jacobian matrix and the inverse of that. So computationally, you know, the size of this will be half of the original Jacobian matrix. So the computation of the inverse of this and that is also easier than before. Okay? Any questions? 민재? I didn't explain that. Yeah, actually that is your homework. I'm joking. Next slide, we have that. Okay. So let's see why that is true. Of diagonal Jacobian terms, so angle and real power are coupled. Yeah, angle and real power are coupled closely, and the voltage magnitude and reactive power are coupled closely. And that is because, you know, in reality, okay, so we have transmission tower. Transmission tower, this is ground, 0 voltage, and transmission line, and it has some resistance and some inductance and some capacitance, you know, shunt capacitance here and here. So you remember the pi model. But okay, so Z equals R plus JX. This resistance is negligible compared to X. So in most cases, we have this relationship. Okay? The reactance component is dominant compared to this resistance component. So that's why in your toy example, the impedance of the two line is like a J.1. No conductance, no resistance component. Okay, and also, please don't be confused that when the impedance, this is impedance, and then admittance is the inverse of the impedance. Because this is inverse of, so the admittance is the inverse of the impedance, you may think, hey, if this reactance is huge, the imaginary part of the admittance would be small, obviously. And maybe similarly, if you think, hey, if this resistance is small or 0, the conductance is huge. Is that correct? Is that correct? Really? So this is right? And this is m to r minus jx over r square plus x squared, right? And then this is the real part, conductance, and then this is susceptance, right? And if we have this relationship, anyway, this is very small. Okay, when even though R is very small, we have very little resistance. The conductance is also small because X is dominant. But when you focus on this imaginary part, this is negligible. So the imaginary part, the susceptance is 1 over X. Okay, so when this inductance component or reactance component is high, our admittance becomes smaller. Okay. Am I saying correctly? Yeah. And so usually, we have this relationship. So this G conductance is 0, can be assumed to be 0. So this B is dominant. Okay. Similarly, we only have this part. So this is a B part, right? This is G part, and this is almost 0. Okay. And also, the phase angle difference between two buses is usually small. So theta ij is small, so sometimes we just ignore this part. Okay. Using these two assumptions, and this is the original power balance equation, and just plug in G0, Gij equals 0, and this is also phase angle difference is small, then it becomes 0. So here we want to, we have power balance equation and take the derivative with respect to voltage, and then you have this result, okay? And yeah, this is almost 0. This is almost, so this is 0. That means our active power does not change when this voltage magnitude changes. Similarly, you have a reactive power equation, and then take the derivative with respect to phase angle, then you have this result. And anyway, this is 0. And yeah, this is also 0, so 0. So reactive power is almost independent of phase angle, mathematically. Assuming this. And in reality, no, this is a reasonable assumption. I saved your homework problem.
DC 파워 플로우를 풀 때 가정이 비슷해 보이는
Yeah. So the most simple approximation is this power flow, and it also assumes the same thing. Okay, so we are our simplification is going on, and finally we will go to this point. We are currently here.
Decoupled power flow와 DC 파워 플로우는
They are different. Okay. The reason is because in this decoupled power flow, we still have reactive power. We still consider reactive power. But in this DC power flow, we completely ignore reactive power. We only focus on active power. Okay, so finally, here the theta is given like this. We only focus on active power and the phase angle. And the admittance matrix and the imaginary part is B. Okay. Good question. Any other questions? So this is the region of convergence of decoupled Newton-Raphson. Yeah, high voltage convergence region, low voltage convergence region. Here they are mixed together, high voltage, low voltage, and divergence case. Okay. Okay, next topic is fast decoupled power flow, FDPF. I think it was introduced, Kyung-Young, I think in your paper, not your paper, the paper you presented before used this kind of concept before, right? Or not, I'm not sure. There was not this. Did we cover FDPF in power system economics or not? You don't remember. Okay, then we will see that in detail. So fast decoupled power flow is about, by further approximating the Jacobian, we obtain a typically reasonable approximation that is independent of voltage magnitude and angle. Ooh. So this means the Jacobian is only be built and factorized once. Okay, it is not updated. And this approach is known as the fast decoupled power flow, FDPF. So FDPF uses the same mismatch equations as standard power flow, so it should have same solution if it converges. And this FDPF is widely used, particularly when we only need an approximated solution. Okay. So, yeah, this is the assumption of FDPF. Again, the conductance is 0. Conductance is 0 because resistance is 0. Okay. When resistance is 0, conductance is not infinite. When we do not have a reactive component, that is true, but here that's not. And another assumption is voltage magnitude is 1. And again, this angle is very small, so sine theta equals 0, cosine theta, the phase angle difference is 1. And then, what is it? Originally we have this. Delta theta minus around P theta inverse delta P x V. And here, this is further simplified, yeah, this part. We do not need to compute the Jacobian of active power with respect to phase angle, but that is replaced by this one. And that is because of that assumption. And similarly, this voltage is expressed, originally voltage, when this is a voltage magnitude, we have a Jacobian of reactive power with respect to voltage magnitude, but that is also replaced by this one. Okay? So anyway, during this iteration, the angle and voltage magnitude updates. Okay? And using that theta and V, the active power and reactive power of all nodes are computed, need to be computed. Okay? But, yeah. And anyway, this is a matrix, but no, this is a diagonal matrix where the diagonal component is the voltage magnitude. So the inverse of the diagonal matrix is very easy, just the inverse of each element. So the inverse of Jacobian becomes very simple, okay? So this method is called FDPF. Again, where B is just the imaginary part of our Y-bus matrix, this one. And here, the slack bus is omitted because slack bus has 0 degree and voltage magnitude 1, so we don't need to compute that. That is just fixed. Okay. So this B matrix is similar to the imaginary part of our Y-bus matrix, except the slack bus, that column, that row and that column is removed. Okay, so yeah, B is B bus, but with the slack bus, row and column deleted. And sometimes, hey, anyway, will be very close to 1. So why do we need to compute it? Just this is the identity matrix. That is another types of approximation. Okay, so this is an example of FDPF. Three bus case. Here again, there is no resistance component on each line. What is the name of this bus? Oh yeah, this is slack bus, not PV bus. At least we need to have one slack bus. Okay, and 2 load buses. And then, you know how to construct this Y-bus matrix? Taesop? You know that? How can you compute it?
1번에서 2번 버스로 이어지는 라인은 5.57.
Yes. Okay, so this is the sum of all the admittance connected to bus 1, right? Okay, so we have the Y-bus matrix. And then from here, our B matrix is just this part, this part, the imaginary part of that. And, we need to remove the slack bus, column, and row. So this is our B matrix. Oh yeah, so that's B inverse is that. And just do the iteration. Theta and V. And when you do that, when you do that, anyway, you compute this one. The voltage is updated. Okay, so yeah, do the iteration. Again. And also during that, you need to compute this part, the active power and reactive power. Okay. So that should be computed, and that is here. So during this iteration, this part, yeah, this is active power or reactive power. So just plug in and you get this solution. So do this on your own by this Thursday. Simple. Okay. This is simple, so do this on your own by this Thursday. And this is the region of convergence. It does not converge to a low voltage solution. It converges to a high voltage solution, and the convergence region is pretty wider than before. But still, in this case, this is a mixture of convergence and divergence. Okay. Finally, DC power flow. And even though we have a concept of decoupled power flow and fast decoupled power flow, in reality, mostly we are using this DC power flow. Okay? And KPX, ISO, yeah, they solve DC power flow for thousands of buses. Okay, and please do not be confused from that naming. DC power flow does not mean DC power flow. Okay, this is still AC system. Okay, and the reason why we are using DC power flow is because of what? We ignore reactive power. We only focus on active power, okay? Because we ignore reactive power, the naming is DC power flow. I don't like that naming because that assumes our power system is AC power systems. That was true, but now we have DC distribution network, DC microgrid, DC high voltage DC connection. And in that case, they also have power flow, right? So the naming is confusing. Anyway, here, this power flow assumes AC power systems, okay? So completely ignore reactive power, assume that all voltages are always 1.0 per unit, and ignore line conductance. Again, yeah, we ignore line conductance, means zero resistance on the line, okay? And this makes the power flow a linear set of equations given like this. Phase angle is just the inverse of B matrix times active power P. Okay. So let's see. We do not have a derivation for this. Just this is the result. Assuming that this is the result. Okay. If I give you one more homework for this derivation, you will be angry at me. So, yeah, and this is our final result. You need to remember. Okay. Yeah, just that equation. Approximation, 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 and final approximation is no iteration. There is no iteration at all. There is no concept of Jacobian, right? Voltage is just one, gone. The reason is because, again, P, theta, Q, V, they are related. They are related. So we are only focusing on this one. It's because we do not care about this reactive power. Voltage is also just assumed to be always 1.0. Okay? So from this DC power flow, when we have Y bus matrix, we have a B matrix, and you can compute the reactive the inverse of that. So and yeah. And this P is active power of all buses except the slack bus. So anyway, you determine the phase angle of all the buses. And anyway, the magnitude is 1.0. Then roughly, using this theta phase angle, you can determine the power flow of each line, I and J, right? The power flow of the active power flow on each line, Ij, approximately. So the heart of DC power flow, this is famous, is what? This computation. The computation of the inverse of this susceptance matrix. Then what is a difficult part here? Sometimes some component of this matrix B can be very small. Okay, and sometimes this matrix B is ill-conditioned. Okay? Anyway, we need to compute this inverse of that. So it can be sensitive to that. And I heard that the ISO in Korea solves DC power flow for more than 4,000 buses in a few seconds. Okay, so they are proud of that. But anyway, from academic point of view, you may want to try solving this DC power flow using deep learning. Okay? So this is an example of a 5-bus system, this one. So 1, 2, 3, 4, 5. Bus 1 is again slack bus, so magnitude is 1.0, degree is 0. And then do we have line impedance information here? Anyway, so you have this B matrix and the active power at bus 2, 3, bus 2, load, bus 3, generator, 4, 5, no load over generator. And here, 8. So that active power, it is based on PU, so it should be normalized by something. And the different sign is because this is load bus and this is generator bus. So yeah, just take the inverse of this, and the phase angle is given like that in radian or degree. But the result, when you look at the result, the degree is 18.7. So then the angle difference between two nodes can be 18 degrees. That's not small. So sine 18 degree. How much is it? Can you compute? Is it close to 0? How much is it? Point. Ooh, huge. 0.309. So this is the result. Okay. So that is because this is just an approximation. Okay. Any questions so far? You do not look happy. You do not look happy, so questions? Why are there so many approximations here? So you are not happy. Okay. So maybe, hopefully, using deep learning, you can get more exact solution. Okay. But again, I'm emphasizing, this is used a lot. It is used a lot in real system, and we will see why in next slide. Next topic is about power system control. So we have a new keyword, control, here. So far, the power system is given. What is given? For PQ bus, the load bus, this PQ is given. For generator bus, this PV is given, right? These two things are given. So we need to satisfy our customers, the load requirement. So we need to supply some active power from the generators. And also we have a slack bus. So there is no control part so far, Newton-Raphson. No control, just solving equation, given, just solve, and then power flows, and then we can satisfy the customer's requirement. And anyway, we have a slack bus. Okay. So the the required active and reactive power can be supplied from this slack bus anyway. Then what is missing here? There is a very important concept is missing when we solve power flow equations. What is that? Minsu, what is that? Hey, come on. Again, so do I need to draw this figure again? Ground, transmission line. Okay, so now we have a network. We solve power flow equations and then power flows. What is missing here? Physically. Each line has its own limit because of the thermal, okay, because of the heat dissipation on this line. This is really important. Okay, so heat is generated, heat dissipation, and then that is because we have a small resistance component. For the approximation, we ignore that R part, R plus Jx, we ignore this, but anyway, in reality, we have this resistance component. So when current flows, heat is generated, then temperature goes up and this line sags, right? And then it may hit the tree and fire can occur. So each transmission line has its maximum transmission limit. But when you solve this equation, we do not have that constraint. In reality, we have constraint. So the solution of this power flow, Pij. So actually, when you solve this power flow equation, you determine theta and V. Or simply just the complex voltage at each node, right? Then we have a topology, we know the complex voltage, and then we can determine the current on each line and the complex power on that line, right? But if there is too much power flow on some line that may exceed the limit of the transmission line, heat is generated, okay? So that's a problem. So when you solve Newton-Raphson, we just ignored or assume that each line has infinite capacity, but that's not true. So that's why we need to have the concept of control. And basically solve it using Newton-Raphson or dishonest or DC power flow, solve the power flow equation, and then compute the Pij and Qij, and check whether it exceeds the limit on this line. And if you find that if some of the line is congested means it delivers more power than it should have. Okay? Then what should we do? If the solution of power flow is the limit, upper limit like this, then what can you do? Which part do you need to change? What should be our control variable now? Well, this is power system control. If the solution cannot satisfy this requirement, this constraint, what you should change? Okay, interesting answer. You want to change theta? Okay. Minje? Of which one? This is a generator. This is load. Yeah, so which P do you want to change? Yeah, you can change this. You may want to change it by calling a factory manager, hey, do not consume so much active power. They can do that. Yeah, that is called demand response. Okay, that is possible, but typically, the operator want to change the active power of the generator. Okay, so before you solve power flow equation, the generator output is already determined, like the maximum or just 80% of the generator. Okay, so we have hundreds of generators in Korea. The output power of the generator is determined somehow. But when you solve power flow equation and find that some line is congested, then you need to adjust the generation amount. Okay? And that's why KPX or ISO first need to solve this DC power flow quickly to check whether some line is congested or not. Okay? So the solution of this DC power flow, of course this is an approximate solution, but anyway, this is good to check whether some line is congested or not. Okay? And then if we find that some line is congested, actually in your power world you can see that here, not here, yeah, here, in this 3-bus system, yeah, 60%, 73%, but 124%. This is saturated actually. The power flow exceeds the limit of this line capacity. Okay. So yeah, in this 3-bus example, 1, 2, 3. This is slack bus, PV bus, and PQ bus. And yeah, here all the active power is supplied from this slack bus. And there is no resistance, so no active power losses on this transmission line. So this 200 megawatt is supplied from this slack bus, but that causes this congestion. So then what should you do? Some of the active power should be generated from here. Okay? And then what you can do is just increase the active power up, 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 up. And finally, this can be just 100%, not exceeds the limits. So that is this one. Yeah, the overloaded line becomes not overloaded when you increase the active power generation here, 95 megawatt. So this is 104 megawatt, 5 megawatt. Okay. So this is kind of control. But yeah, this is a kind of control. Then next question is, okay, after we solve power flow equation, either honest Newton-Raphson or that or that or that, we found some line is congested. So I want to change the output of the generators. How can you find the output of generator that ensure that all the lines are not overloaded? That's not an easy job. If you are an experienced operator, you may know how to do that, okay, by trial and error for many years. But we want to have the solution systematically, okay? So, to do that, we have a concept of sensitivities. What is the meaning of sensitivity? The meaning of sensitivity here is that if you inject more power in some generator, where is it? Yeah, here. By the way, let's read what it says. Power system control. A major problem with power system operation is the limited capacity of the transmission system. Line, as well as transformers have limits, usually thermal limits, and no direct way of controlling flow down a transmission line. Too close to limit flow, except on off. But open transmission system access associated with industry restructuring is stressing the system in new ways. So we need to indirectly control transmission line flow by changing the generator outputs. So this is the concept, indirect transmission line control. So after we discuss this, anyway, we will go to optimal power flow part. But this is not yet optimal power flow. Okay? So here, what we want to do is we have a power system network, and we have a generator at bus K, and this is some line between I and J. Then we want to quantify when you inject a unit power at some generator, how much the power flow on this line of our interest, I and J, increase or decrease. Okay? That is the concept of sensitivity. So what we would like to determine is how a change in generation at bus K affects the power flow on a line from bus I to bus J. Okay? And here, the assumption is that the change in generation is observed by the slack bus. The meaning of observed means that you can freely increase or decrease the generator output because anyway the slack bus can compensate it. Okay? So yeah. Analytic calculation of sensitivities. Calculating control sensitivities by repeated power flow solution is tedious. You can do try and error, but that's not a systematic way and would require many power flow solutions. An alternative approach or systematic approach is to analytically calculate these values. So the power flow from bus I to J is approximated like this. It depends on the voltage magnitude and the phase angle difference. And further simplified like this. Anyway, this is close to 1. And anyway, this is close to 0. So approximated like this. And the difference of power flow is the difference of the phase angle given like this. Okay? So we just need to get when the phase angle changes, how much when the amount of generation changes, how much this phase angle changes. Okay, so as long as we know this, we can solve the problem easily. So to do that, anyway, so this is based on DC power flow. So either using this equation or they put just delta notation to emphasize the update of angle and active power. Okay, so here we need to see when we have many generators, we don't know which generator, which generator should increase their output. So the generator of interest is denoted by 1 or -1. And the convention here is -1 is increase of the generation. I don't know why, but they say that's the convention. Okay? This negative sign is for 1 megawatt increase in generator at bus K. Okay, so when this, our generator of interest increases the output, using that DC power flow update rule, not update, just the equation, the phase angle is updated, determined. So I think this should be our last slide. Yes. So for the previous 3-bus system, the impedance is J.1. We have the Y bus matrix. From that, eliminate the first row and first column and have the B matrix. And the phase angle change is computed. And changes in line flows are, what is it? So yeah, 3-to-1 or P3-1. P3-2, P2-1 is what? Yeah, so our approximated solution, the power is determined from here. So when you compute the angle, from that you can compute the power. So that's this. So using DC power flow, you compute the phase angle, and from that, you can check the increase or decrease power on each line, 3, 1, or 3, 2, or 2, 1. Okay. Well, and this is about the sensitivity. Not exactly, not quite clear how can we solve systematically the congested line. But anyway, we can use this information. So let me stop here. And next.